And here, since we have some functional form for the displacement x as a function of t, okay, in this form. So we can substitute it into the expression here. Then we also get a functional form of the potential energy, okay, as a function of the time t. So you can check it's 1/2 k xm squared cosine, okay, squared. Okay, that's a cosine squared. You just square the position function here. So here, for the potential energy, we can know the potential energy at any time. Okay? It's a function of time t. Now, if we look at the kinetic energy, the kinetic energy, okay, since the object is in motion, so it has a kinetic energy. Kinetic energy is 1/2 mv squared. Okay? And we also have some function as a time for the velocity. So if we substitute this v to here and square it, we can get the expression for the kinetic energy as a function of time t. Okay, 1/2. Okay, let's do it. So if we square that, it will kill the negative side. You are going to get omega squared xm squared, okay, multiplied by sine squared, right?
Do you still need the mass in there?
Okay, you still, yes, I still have the mass here. Okay. Now, so here we can do some simplification, m omega squared, by using this. Okay. From this equation, you can see that if you take the square, we get omega squared equals to k over m. So omega squared multiplied by m equals to k, right? So here, this quantity is actually k. So we get now if you compare the potential energy and the kinetic energy as a function of time, okay, see here the prefactor will be the same, 1/2 k xm squared, and then it's modified, this one is modified by a cosine squared, this one is modified by a sine squared. Okay. So the form of the two energies looks very similar to each other. So the same factor multiplied by cosine squared or sine squared. Okay. So that's the potential energy and the kinetic energy. Okay. And now let's look at one more thing. If we try to calculate the mechanical energy for the system, okay, so it should be potential energy plus the kinetic energy, right? So it will be this one plus this one. So I can factor out 1/2 km squared. So it's 1/2 km squared multiplied by cosine squared plus sine squared. Okay, with the same angle here. What's this? Cosine squared plus sine squared. It's 1. This is the identity. For the same angle, cosine squared plus sine squared is always 1, right? Okay, this is an important trigonometry identity. Sine x, okay, any angle, say x squared plus cosine x squared equals to 1. Okay, for any arbitrary angle. So this equals to 1. That means mechanical energy equals to 1/2 km squared xm squared. This is the total mechanical energy for the spring system. And something you can see here. Originally, I expect it may be a function of the time because u is a function of time, k is a function of time. But after calculation, it seems that the mechanical energy is not a function of time because the time dependence is killed by the identity here, right? Okay, so that means the change in this part always compensates the change in this part. So this is a constant. And this is understandable, right? Spring system, mechanical energy is conserved. So at any time, it should take same value. It should take the same value. Okay. So there is no dependence on time. Okay. So this expression, in fact, is just a more detailed example for the general mechanical energy conservation for a spring system. Okay. Any question here? Now, let's look at more about the energy conservation. So we know that if you have a spring system, there are some spatial points has a particular interest for us. The equilibrium position at the maximum displacement position. Okay. So if you have a spring system, if this is the equilibrium position x0, okay, and it can be stretched to a maximum position x m, or in the other direction, okay, it can be compressed. This is also xm, okay. Should be the same, okay, at both sides. Okay. So we know that at the center, okay, the center of the oscillation or the equilibrium position, the displacement x0 equals to 0, right? But you reach the maximum velocity, Vm, and here. So, okay, so V0 equals to Vm. At this point and this point, the displacement x equals to maximum value. But how about the velocity at this, and here, and here? 0. Okay. And now, if you calculate the potential, the mechanical energy at this point, so E, if you just directly use our definition for the mechanical energy, should be 1/2 mv squared plus 1/2 kx squared, right? At this point. So the same as this point. So this is 0 plus 1/2 kxm squared. Okay. So it directly give you the value supposed to be. At any point, it should be this one. Okay. Now, if you calculate the mechanical energy and the equilibrium position here, okay, let's go to E0. This is for here. This is for here. It will be 1/2 mv0 squared plus 1/2 k x squared, x0 squared, right? So it will be 1/2 mv0 squared plus 0. And here v0 is Vm, maximum velocity. Okay. So in fact, if you apply this and equate with this mechanical energy, okay? Because anywhere the mechanical energy should be the same as the constant value, right? So in fact, you can get this 1/2 mvm squared equals to 1/2 k xm squared. It gives you the relationship between the maximum velocity and the amplitude, which is maximum relation. Okay. So this amplitude here tells you determines the maximum velocity here. Okay, for the oscillation. Any question here? This is just an application of the mechanical energy in the usual way. If you consider this is your initial state, this is your final state. Write down the mechanical energy conservation. Okay. So here you have to be very clear about this conceptual stuff. Okay. If you solve a problem for the simple harmonic motion, you can see there's a lot of quantities involved, a lot of equations involved. So if you don't have a clear conceptual understanding, it's hard to figure out the right equation. Okay? Now, let's